Okay, so last example here of angular momentum conservation. Didn't draw the details, too complicated, but this is a merry-go-round. Bird's eye view, merry-go-round, sitting still, nothing happening, just a merry-go-round. Sitting there in the playground somewhere. It's got a mass of 232 kilograms. It's got a radius of 2.10 meters. And this kid, mass M, 34.0 kilograms, starts running right towards the edge of it, is going to jump up on it and grab hold of it and start going around. Right? He's going to jump on it, and his motion is going to carry the thing forward. The question is, if he's running at 2.80 meters per second towards the edge of it, and when if he's going that speed when he jumps on, what is the final angular speed of the merry-go-round and the kid? That's the question. All right? There's our Cloud-O principles right there. Angular momentum conservation. LF equals LI. And you know what L equals, right? L is I omega. Okay? So let's do it. What is the initial angular momentum? Li. Let's do it right here. Li equals what? Well, this is like the car 2 videos ago. The kid is running along a line, right? Not right at the point, but running along a line beside the point, right? So it's going to be M V R perpendicular, which in this case happens to be R, the radius of the wheel itself. Remember, it was down here, the red car moving that way. The point up here, the red car has an angular momentum around any point you pick. We're interested now in the angular momentum of this kid running in a straight line, but we're going to measure the angular momentum around that axis right there in the middle of the merry-go-round. So this is just equal to mvr because the perpendicular distance, r perpendicular, is equal to the radius of the wheel, which is 2.10 meters. That's the initial angular momentum, right? Because the wheel's not turning, it's just chilling, so there's no motion, there's no angular momentum of the wheel. It's just sitting there. So that's it. That's the total initial angular momentum. That is all. Okay? And then the kid's going to latch on, and the kid and the wheel are going to move together. So what is the final angular momentum of the wheel and the kid? Okay, what is it? Well, here we have to step back a little bit and think about the very definition of angular momentum itself. We already took care of this case earlier. The case of the straight line motion. We took care of that case earlier. But here we have a big disc, right? Just think of it like a big disc. Don't worry about the handles and stuff on it. Just think of it like a big disc of mass big M and radius R. So we have to go back to first principles. We know that this is going to be equal to I times omega. Now this is the omega we're solving for, right? That's going to be the final omega. That's omega. But the question is, how do we find the moment of inertia here of a flat disk and a kid on it? So the moment of inertia is going to be equal to the moment of inertia of the disk, that is, of the Ferris wheel itself, not Ferris wheel, merry-go-round. Okay. What do you call the, is merry-go-round even the right name for this? Carousel. No, merry-go-round is right. Carousel is the big thing with all the animals on it, right? And the gold ring and all that. That's a carousel. This is a merry-go-round, little thing you see out on the playground. That's right. So this is the merry-go-round. The total moment of inertia is going to be the moment of inertia of the merry-go-round, the disc, plus the the moment of inertia of the child. And again, disk is, I could have written merry-go-round instead. Just imagine it like a big disk with that mass and that radius. Okay, so what is it? Well, I have the disk of any disk. If you go back and look at last chapter, it's going to be 1/2 mr squared. That is the moment of inertia for any disk spinning around its center. We did an example with a rolling disk, and we used that for its moment of inertia. Earlier this week, maybe late last week, I can't remember. It all kind of blurs together. Okay, so what's the moment of inertia of the child? Now, the child is latched on to the disk and is moving around with it. Okay. So what is it? Well, it turns out it is mr squared. Again, if you go back to the earlier section, I don't remember the page number where we did it, but a single point mass moving in a circle around the middle of the circle, moving in a circle, the moment of inertia is mr squared. So you'd have to look both those up, but you could do that. That would be given to you, free of charge. So that's the total moment of inertia. Okay, so now we can substitute all this in, and we can write LF is going to be 1/2 mr squared plus little m r squared, where little m is the mass of the kid, 34 kilograms, times omega. We just had to work on the moment of inertia a little bit, that's all. That's all. So what we have is we have Li here, we have initial moment of inertia there, we have final moment of inertia there, and our cloud of principles tells us, aha, they're equal. Boom, so let's write it down. They're equal. So LF, let's write it down, is 1/2 mr squared plus little mr squared, all that, times omega. It's equal to the initial momentum, which is just little m v r. That's Li. Lovely. Okay. And we need to solve this for omega. We know everything else. But do notice that we can do a little bit of a simplicity here. We can cancel out one factor of r everywhere. Shows up squared in these terms, shows up linearly, that is to the power of 1 in this term, so we can cancel all that. So if we want to isolate omega, all we do is divide out all this stuff. So omega is going to be equal to little m v over 1/2 big M R plus little m r. Okay, so that is, let's see, little m is 34.0 kgs times velocity speed, which is 2.80 meters per second, divided by, squeak, 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 1/2 times this big old number, 232, times R, which is 2.1 meters, plus little m, which is 34.0, beautiful, 34.0 kilograms times 2.10 meters. Multiply it all together, divide it, add it, subtract it. What you get is omega. There's only no subtraction to do in there. You get omega is 0.306 radians per second. 0.306 radians per second. Which is really slow. Not too fun. This kid will want to get some friends along to help move him a little bit faster. That's like this. Let's see. That's like about that fast. Not a whole lot of fun. But the math was fun. The physics was fun, right? So there you go. Conservation of angular momentum. Okay. Trickiest part is realizing that the kid had an angular momentum to start with. Again, it's not intuitive that somebody running in a straight line would have angular momentum at all. But angular momentum is always measured with respect to a certain point. Okay? Just like when we do torque, we can always pick our axis. We always pick our axis here also. Natural spot point here was the very center of this wheel. Didn't have to use that. We could use any point we wanted to, but that's the natural, simplest one to pick. So we do, and the kid's angular momentum around that point is given by MVR. Okay, that's it. That, and with the fact that we had to break out the moment of inertia into two pieces. Okay, the total moment of inertia of the kid and the wheel, you had to add them up separately. The moment of inertia of the wheel plus the moment of inertia of the kid, which is what we did right there. All right, that is all. See you next time.